Carbon and hydrogen are the chief elements present in an organic compound. In addition to these elements, an organic compound may also consist of other elements such as nitrogen, oxygen, sulfur, halogens, phosphorus, and so on. The qualitative analysis helps to detect the presence of these elements present in an organic compound. Let us look at how the elements carbon and hydrogen are detected. First, the given compound is heated with the oxidizing agent cupric oxide. As a result, the elements carbon and hydrogen present in the compound get oxidized to carbon dioxide and water respectively. The products obtained are then passed over anhydrous copper sulfate and bubbled through lime water. We observe that copper sulfate turns blue, whereas lime water turns milky. Anhydrous copper sulfate absorbs moisture and turns blue due to the formation of hydrated copper sulfate, that is, copper sulfate pentahydrate. This indicates the presence of hydrogen. When the carbon dioxide formed in the reaction is passed through lime water, that is, calcium hydroxide, a milky white precipitate is formed due to the formation of calcium carbonate. This indicates the presence of carbon in the given compound. Now, let us look at the detection of other elements such as nitrogen, sulfur, and halogens. The presence of nitrogen, sulfur, and halogens can be detected using Lassigne's test. In Lassigne's test, a small piece of sodium metal is taken into a fusion tube and is heated to red hot. Then, the given compound is added to it in small amounts and the fusion tube is again gently heated to red hot. The red hot tube is then introduced into a mortar containing a few ml of distilled water. The red hot tube is crushed and the mixture is thoroughly grinded with the pestle. The contents are then filtered into a test tube. The filtrate obtained is called sodium fusion extract or Lassigne's extract. This extract is used to detect the other elements such as nitrogen, halogens, and sulfur. During fusion, the elements nitrogen, sulfur, and halogen combine with sodium and are converted to sodium cyanide, sodium sulfide, and sodium halide respectively. In other words, they are converted into their ionic forms. Carbon and nitrogen present in the organic compound react with sodium metal to form sodium cyanide. If sulfur is present in the compound, it is converted to sodium sulfide, whereas the halogen in the compound is converted to respective sodium halide. Now, for the detection of nitrogen, a small amount of sodium fusion extract is boiled with a pinch of solid ferrous sulfate and then acidified with concentrated sulfuric acid. The sodium cyanide reacts with ferrous sulfate to form sodium hexacyanoferrate 2. Ferrous ions are oxidized to ferric ions when heated with concentrated sulfuric acid. These ferric ions react with sodium hexacyanoferrate 2 to produce Prussian blue coloration of ferriferrocyanide, that is, iron 3 hexacyanoferrate 2. The Prussian blue coloration confirms the presence of nitrogen in the organic compound. There are two tests that help us to detect the presence of sulfur using sodium fusion extract. The first test involves the reaction between the sodium fusion extract and lead acetate, whereas the other involves the reaction between sodium fusion extract and alcoholic sodium nitroprusside. In the lead acetate test, sodium fusion extract is first acidified with acetic acid and later lead acetate solution is added to this mixture. This produces a black precipitate of lead sulfide, confirming the presence of sulfur. In the sodium nitroprusside test, the sodium fusion extract is treated with a few ml of alcoholic sodium nitroprusside. If the mixture turns violet, it indicates the presence of sulfur. The violet coloration is due to the formation of sodium thionitroprusside. If nitrogen and sulfur both are present in the organic compound, then on heating the sodium fusion extract with acidified ferrous sulfate solution, a blood red coloration is obtained instead of Persian blue. The blood red coloration is due to the formation of sodium thiocyanate ion 3, thus indicating the presence of both nitrogen and sulfur. In the test for halogens, sodium fusion extract is first boiled with dilute nitric acid. To this solution, a few drops of silver nitrate solution are added. The color of the precipitate indicates the presence of the specific halogen. A white precipitate, soluble in ammonium hydroxide, indicates the presence of chlorine. The white-colored precipitate is due to the formation of silver chloride. If the precipitate is pale yellow and sparingly soluble in ammonium hydroxide, then it indicates the presence of bromine. The yellow-colored precipitate is due to the formation of silver bromide. If the precipitate is yellow and insoluble in ammonium hydroxide, then it shows the presence of iodine. This yellow-colored precipitate is due to the formation of silver iodide. To detect the presence of phosphorus, sodium extract is heated with oxidizing agent sodium peroxide. And then treat it with ammonium molybdate. If a yellow precipitate of ammonium phosphomolybdate is formed, it indicates the presence of phosphorus. In the test for halogens, sodium fusion extract is first boiled with dilute nitric acid. To this solution, a few drops of silver nitrate solution are added. The color of the precipitate indicates the presence of the specific halogen. A white precipitate, soluble in ammonium hydroxide, indicates the presence of chlorine. The white-colored precipitate is due to the formation of silver chloride. If the precipitate is pale yellow and sparingly soluble in ammonium hydroxide, then it indicates the presence of bromine. The yellow-colored precipitate is due to the formation of silver bromide. If the precipitate is yellow and insoluble in ammonium hydroxide, then it shows the presence of iodine. This yellow-colored precipitate is due to the formation of silver iodide. To detect the presence of phosphorus, sodium extract is heated with oxidizing agent sodium peroxide. And then treated with ammonium molybdate. If a yellow precipitate of ammonium phosphomolybdate is formed, it indicates the presence of phosphorus. First, let us see the method of estimation of carbon and hydrogen in an organic compound. Carbon and hydrogen in the organic compound are estimated by Liebig's method. The apparatus used for this method consists of a combustion tube packed with copper oxide pellets, a platinum or porcelain boat, 2 pre-weighed absorption tubes, and a burner. In this method, a known quantity of the organic compound is placed in the platinum or porcelain boat. The boat is placed in the glass combustion tube packed with copper 2 oxide pellets. One end of the combustion tube is connected to the oxygen supply, and the other side is connected to the 2 U-shaped absorption tubes. One of the absorption tubes contains anhydrous calcium chloride, while the other contains concentrated potassium hydroxide solution. Now, the combustion tube, along with the boat placed in it, is heated and pure oxygen is passed through it. As a result of combustion, carbon dioxide and water are formed. Water in the mixture is absorbed in U-tube containing anhydrous calcium chloride, and carbon dioxide is absorbed in another U-tube containing concentrated solution of potassium hydroxide. The U-tubes are weighed again after this absorption. The increase in the masses of calcium chloride and potassium hydroxide is calculated to get the amount of carbon dioxide and water in it. From the amount of carbon dioxide and water, the percentage of carbon and hydrogen are calculated. Let the mass of the organic compound taken be m grams, and the mass of the water and carbon dioxide produced be m1 and m2 grams, respectively. We know that 44 grams of carbon dioxide contains 12 grams of carbon. Therefore, the carbon content in m2 grams of carbon dioxide may be calculated as 12 multiplied by m2 divided by 44. Now, m grams of organic compound contain 12 multiplied by m2 divided by 44 and m. Therefore, 100 grams of organic compound would contain 12 multiplied by M2 multiplied by 100 divided by the product of 44 and M. This gives the percentage of carbon present in m grams of the given organic compound. The percentage of hydrogen is also calculated in a similar way. We know that 18 grams of water contains 2 grams of hydrogen. Therefore, m1 grams of water contain 2 multiplied by m1 divided by 18. Now, m grams of organic compound contain 2 multiplied by m1 divided by 18 and m grams. Therefore, 100 grams of organic compound would contain 2 multiplied by m1 multiplied by 100 divided by the product of 18 and m. For the estimation of nitrogen, two methods, the Dumas method and Kjeldahl's method, are used. In Dumas method, a known mass of an organic compound is heated strongly with coarse cupric oxide in an atmosphere of carbon dioxide. Carbon and hydrogen get oxidized to carbon dioxide and water, while the nitrogen present in the organic compound is converted into free nitrogen. A part of the nitrogen may get oxidized into oxides of nitrogen. When passed over a heated copper gauge, these oxides of nitrogen are reduced into free nitrogen again. The mixture produced, which contains carbon dioxide, water, and nitrogen, is collected over an aqueous solution of potassium hydroxide. This solution absorbs the carbon dioxide gas from the mixture, leaving nitrogen behind. This nitrogen is collected in the upper part of the graduated tube. From the volume of this nitrogen collected, the percentage of nitrogen in the compound is calculated. If the mass of the organic compound is m grams, the volume of the nitrogen collected is V1 ml at room temperature of T1 Kelvin. The atmospheric pressure is P and the aqueous tension at T Kelvin is P dash. Then, the pressure of nitrogen gas at T Kelvin is atmospheric pressure P minus aqueous tension P dash. Let this be equal to P1. Then, the volume of nitrogen at STP is equal to P1 mm multiplied V1 ml multiplied by 273 Kelvin divided by the product of T1 Kelvin and 760 mm. Let's assume that the resultant volume is VML. As we know, 22,400 ml of nitrogen weigh 28 grams at STP. Therefore, VML nitrogen at STP weighs 28 multiplied by VML divided by 22,400 ml. Nitrogen is also estimated by another method known as the Kjeldahl's method. The method can be divided into two major stages, namely digestion and distillation. During the digestion stage, the nitrogen present in the organic compound is converted into ammonium sulfate. This is achieved by heating the compound in Kjeldahl flask with concentrated sulfuric acid in the presence of small amount of copper sulfate. Now, the contents of the flask are cooled and transferred into a distillation flask and heated with concentrated sodium hydroxide to liberate ammonia gas. This is the distillation stage. The ammonia produced in this process is absorbed in a known volume of excess of standard solution of sulfuric acid. Therefore, the amount of ammonia produced can be determined by estimating the amount of sulfuric acid consumed in the reaction. It is done by estimating the unreacted sulfuric acid left after the absorption of ammonia by titrating it with standard alkali solution. The difference between the initial amount of acid taken and that left after the reaction gives the amount of acid reacted with ammonia. Let's assume that the mass of the organic compound taken is m grams. The volume of sulfuric acid of molarity m taken in the flask is V ml. The volume of sodium hydroxide of molarity m used for the neutralization of excess acid is V1 ml. As per the stoichiometric equation, V1 ml of sodium hydroxide of molarity m is equal to V1 by 2 ml of sulfuric acid of molarity m. The volume of the unreacted sulfuric acid of molarity m is equal to V minus V1 by 2 ml. V minus V1 by 2 ml of sulfuric acid of molarity m is equal to 2 multiplied by V minus V1 by 2 ml of ammonia solution of molarity m. From the equation, we get that this is equal to twice the volume of the ammonium solution of molarity m. We know that 1000 ml of 1 molar ammonia solution contains 17 grams of ammonia or 14 grams of nitrogen. Therefore, 2 multiplied by V minus V1 by 2 ml of ammonia solution of molarity m contains 14 multiplied by m multiplied by 2 multiplied by V minus V1 by 2 divided by 1000. Therefore, the percentage of nitrogen is equal to 14 into m into twice V minus V1 by 2 divided by 1000 and multiplied by 100 by m. It is important to note that Geldahl method is not applicable when nitrogen is present in the ring, as well as in nitro and azo compounds. This is because the nitrogen of these compounds does not change to ammonia sulfate under these conditions. Halogens are estimated by Carius method. In this method, a known mass of organic compound is to be heated with fuming nitric acid in the presence of silver nitrate in a hard glass tube called Carius tube. In this process, carbon and hydrogen are oxidized to carbon dioxide and water, while halogen is converted into silver halide. The halogen forms a precipitate of silver halide. This precipitate is filtered, washed, dried, and then weighed. Let the mass of the compound taken is m grams and the mass of the silver halide formed as m1 grams. 1 mole of silver halide contains 1 mole of halide. Therefore, the mass of halogen in m1 of silver halide is determined by dividing the product of the atomic mass of halogen and m1 by the molecular mass of silver halide. Therefore, the percentage of halogen is equal to the atomic mass of halogen multiplied by m1 multiplied by 100 divided by the product of molecular mass of silver halide and m. To estimate sulfur present in the given organic compound, a known mass of the organic compound is taken in a Carius tube and heated with sodium peroxide or fuming nitric acid. The sulfur present in the compound is oxidized to sulfuric acid. The acid is cooled then treated with excess of aqueous barium chloride solution. It gives a precipitate of barium sulfate. This precipitate is filtered, washed, dried, and then weighed for analysis. The percentage of sulfur can be calculated from the mass of barium sulfate. Let the mass of the organic compound taken be m grams. The mass of barium sulfate formed is m1 grams. We know that the molecular mass of barium sulfate is 233 grams. And the amount of sulfur in 1 mole of barium sulfate is 32 grams. Therefore, the mass of sulfur in m1 gram of barium sulfate is m1 multiplied by 32 divided by 233. Therefore, the percentage of sulfur in the compound is 32 multiplied by m1 multiplied by 100 divided by 233 multiplied by m. The quantitative analysis of phosphorus in the given organic compound is done by heating a known mass of organic compound with fuming nitric acid in a carrier's tube. As a result, phosphorus is oxidized to phosphoric acid. When this phosphoric acid is treated with ammonia and ammonium molybdate, a precipitate of ammonium phosphomolybdate is formed. Sometimes, phosphoric acid is precipitated by adding magnesia mixture. Magnesia mixture is obtained by dissolving 100 grams of magnesium chloride hexahydrate and 100 grams of ammonium chloride in water. To this, 50 ml of ammonium hydroxide is added and the solution is diluted to 1000 ml. On adding magnesia mixture to phosphoric acid, a precipitate of magnesium ammonium phosphate is formed. This precipitate is filtered, washed, dried, and then ignited to produce magnesium pyrophosphate. From the weight of magnesium pyrophosphate, weight of phosphorus can be estimated. Let the mass of the organic compound taken be m grams and the mass of ammonium phosphomolybdate be m1 grams. The molecular mass of ammonium phosphomolybdate is 1877 grams. Atomic mass of phosphorus is equal to 31 grams. Therefore, the percentage of phosphorus present in the compound is m1 multiplied by 31 multiplied by 100 divided by the product of 1877 and m. If phosphorus is estimated as magnesium pyrophosphate, then the percentage of phosphorus is equal to 62 multiplied by m1 multiplied by 100 divided by the product of 222 and m. Here, m is the mass of the organic compound taken. m1 is the mass of magnesium pyrophosphate formed. 222 is the molar mass of magnesium pyrophosphate and 62 is the mass of 2 phosphorus atoms present in magnesium pyrophosphate. For the quantitative analysis of oxygen in an organic compound, a known weight of the organic compound is heated in a stream of nitrogen gas. As a result, the organic compound gets decomposed. Then, the oxygen-containing mixture is passed over red-hot coke, where all the oxygen is converted to carbon monoxide according to the equation shown. This gaseous mixture is passed through warm iodine pentoxide when carbon monoxide is oxidized to carbon dioxide, producing iodine. This reaction may be represented as shown here. To make the amount of carbon monoxide produced in the first equation equal to the amount of carbon monoxide used in the second equation, multiply the first and second equation with 5 and 2 respectively. It is clearly evident from the equation that 1 mole of oxygen liberated from the compound produces 2 moles of carbon dioxide. Thus, 88 grams of carbon dioxide is obtained if 32 grams of oxygen is liberated. Let the mass of the organic compound taken be m grams. Mass of carbon dioxide produced be m1 grams. We have seen that 88 grams of carbon dioxide is obtained if 32 grams of oxygen is liberated, and then m1 grams of carbon dioxide is obtained if 32 into m1 divided by 88 grams of oxygen is liberated. Therefore, the amount of oxygen liberated from m grams of organic compound is equal to 32 into m1 divided by 88 multiplied by m. Hence, 100 grams of the compound produces 32 multiplied by m1 multiplied by 100 divided by the product of 88 and m. This gives the percentage of oxygen present in the compound.